So in this video, I want to discuss what I would term the metrics. We can have metrics of a model, metrics as far as a new test is concerned. Later on, I'll talk about the fact that what I'm going to show you in this video lecture can even be applied to the manufacturing world. There's so many places where we can apply metrics. And the metrics that we're going to talk about are sensitivity, specificity, positive and negative predictive values. So we've already looked at probabilities. We looked at joint probabilities, marginal and conditional probabilities. Let's put that knowledge into action when we look at these metrics. Now in the data set that we have here, we see that we have two variables. This is tidy data in long format. So every column is a specific variable, every row is a specific subject. And we see in our first row, we see the two column headers. Those would be the names of our two variables. One is called disease status, and the other one's called test results. So what we're going to imagine here is that we know absolutely whether someone has a disease or does not have a disease. So imagine there's some gold standard test to determine whether someone is suffering from a disease or whether that disease is absent. And what we now do is we evaluate a new test. Maybe this test is cheaper, it's quicker. And we saw this, of course, in the COVID pandemic, where the initial test results took a long time to come out, but new, faster tests were developed. But we need to know whether these things are accurate. When someone actually has the disease, does this test come back positive? And when someone doesn't have the disease, does this test come back negative? So if we have two variables such as these, they are both binary. In other words, there are only two categories. And both of these nominal categorical variables, there's obviously four specific cases that we can get. We can get disease positive, disease negative, and no disease positive and no disease negative. And what we're going to do is create a table of observed data, otherwise known as a contingency table, that are just going to count those four joint frequencies. So someone who's got both disease and positive, someone who's got both disease and negative, and no disease and positive and no disease and negative. And you can see, as far as we go down, you can see those four cases. So I've already made a copy of the data. If we look down at the bottom, we can see original and copy. So we're never going to change or alter the original. We can just make other copies. So I've already made a copy, but now I want to make a brand new sheet. And what I want to do here is call this sheet metrics. So let's go to our original data. I'm just going to copy from there again. Now this data is contiguous, so there's no missing data. Everything is there. There's no missing rows. So I can very quickly just say Command A or Control A, and it'll copy or at least select all of that data. Now I'm going to hold down Command and hit C or Control and C on Windows, and we see the marching ants. We've copied that data. Let's go to metrics, and I'm right there in cell A1. And what I want to do here is go to the Home tab there. I'm going to do paste and all the way down to paste values. I just want to copy those values across. Now remember, what I do like to do, always change this into a table. Let's increase the screen size a little bit. There we go. Let's change this into a table. So I've selected any of the cells. I'm going up to insert, and I'm going to hit table, the third one across. Table. My table does have headers, so I've got to click that little pop-up and say OK. And now we have this in table format. Now to create a contingency table that's going to count these four joint frequencies for me, I've got to create a pivot table. So let's do the pivot table. Again, that's under the insert. And now it's this little first one, pivot table. Now this is already a table, so it's going to be selected for me because I made that effort of changing this into a table. Otherwise, remember, you can always click this little button and then manually select all of your data. Where do I want my pivot table to reside? Well, I want that in this existing worksheet. I've already created a new one specifically for this analysis. So I'm going to click on my little selection button, and let's put this one in E4. Why not? I'm going to click there again to expand, and I'll select that. And now to create my pivot table, I see I have disease status and I have test results. Now let's think about this. The way that we want to construct this contingency table or table of observed data is the fact that we might want the test results to be along the rows and whether someone has the disease or not have the disease along the columns. Of course, you can transpose that and have it the other way around. But for This case, let's take test results and let's drag it down into the rows. So right down there into the rows, and I'm going to drag disease status into the columns area there. And there we can see both are binary categorical variables, because in the rows for test results I have negative and positive, and as far as the disease is concerned, across the columns I have disease right there and no disease. Now I just have to do those 4 frequencies, joint frequencies. So I see 4 open slots here, and for each one of these cells, remember that's a joint frequency. So this first little cell here must be the number of people who were both diseased and had a test result of negative. And over there, I want to know the number of cases down the spreadsheet where someone had no disease in the first column and they had a negative result in the second column. So we can drag any one of these down to values. Let's drag disease status down to values. And we can see it says there, very small, count of disease. And that's exactly what we want. Otherwise, we can click that little I for information and just make sure that it is count. I want the counts, the number of cases or the frequency of those cases. And there we go. Immediately we see a table of observed data. Very quickly, we notice that we have 801 subjects in our data set. And as far as the number of people with disease, that will be this column, there were 318 with the disease and 483 without the disease. And if I look across the row totals, I see that 500 people tested negative and 301 tested positive. And then the 4 joint frequencies. Now we're going to have a look at sensitivity. Let's put it right there. I'm going to look at specificity. And later on, we'll look at positive predictive values and negative predictive values. So those are the 4 metrics that we're going to talk about. The first 2, sensitivity and specificity, is something that we want to know about this test before we decide whether we want to use this test. And the second 2, the positive and negative predictive values, we can use those metrics to interpret once the results are known for a specific subject. So let's start with sensitivity. Now, sensitivity is the proportion of cases with the disease for which the test result came back positive. So let's think about that. It's the proportion of cases with the disease, and we know how many people had the disease. Well, there were 318 with the disease. How many of those actually came back positive? Well, there were 220 of those came back. So what we're doing here, we're using probability and proportion as synonyms. And actually, I like to stick with the term proportions here. This is a sample of data. It's not the whole population. We're not talking about any kind of inference at the moment. We're clearly just calculating the proportion of some whole. When we talk about the proportion of a whole, though, we can express ourselves as using the term probability. But here, clearly, even though those 2 are synonyms for us here, I think it makes more sense just to stick with the word proportion. What proportion of everyone with the disease will this test actually pick up? And we calculate this from this table of observed data. Now, specificity is something else. That is the number of cases without the disease, and there were 483 of those, that the test actually came back negative. So what proportion of people without the disease did this test come back negative? So it indicates the absence of that disease. And what we'll do here on the side is just to remind ourselves of these 4 joint frequencies. If someone really has the disease, but their test is negative, then clearly that is a false negative. So I'm just going to put F in there to remind myself. That's a false negative. This person had the disease, but the results came back negative. That's a false negative. If we look at the 402, those people did not have the disease and the test came back negative. Clearly, that's a true negative. Let's look at this 220. Those were people with the disease and the test came back positive. That's correct. They had a true positive result. And then as far as the 81 is concerned, they did not have the disease, but the result came back positive. That's a false positive. False positive. Let's put FP. Now, depending on your variable and the way that you name the categories inside of those 2 variables, what Excel is going to do, it might put these things in different order. So do not learn some rhyme when you have letters such as A, B, C, D, and then you remember it's AD minus BC. something like that, or A divided by A plus B. Do not learn or try to memorize those little formulae. Rather, look at your data and try to interpret it, because, as I say, depending on what the names are that you gave to these levels or categories inside of your binary categorical variables, Excel is going to put one in front of the other. So as far as the rows are concerned, something will be in the top row, something in the bottom row. As far as the columns, something will be in the left column, something will be in the right column. So rather, think it through. So now that we have that, let's calculate sensitivity and specificity. So what proportion of people with the disease did this test actually pick up? That's the definition of sensitivity. So it's going to be a proportion of some whole. And as I say, when something is a proportion of a whole, we can think of it as a probability. But let's think about this as a proportion. So it was actually 220 cases out of the total of 318 with the disease that this test actually came back positive. So I'm going to click on the 220, and then I'm going to say /, and then I'm going to click on the 318. Now, because I've created a name for the sheet and I've created a table, I get this long reference to each of these cells as I click on them. Don't be worried about that. I'm going to hit return or enter, and we see 220 divided by 318 is 69. So this test picked up 69% of the cases that actually have the disease by returning a positive result. So let's do the same for specificity. So that's going to be the proportion of cases without the disease that this test actually picked up. So it returned a negative result in the cases who really didn't have the disease. So there's a formula. I'm going to start with equal, and then I've got to see what do I divide by what. So clearly in the denominator, it's got to be the 483, but what's in the numerator? Well, the correct ones, the one that the test returned negative, and that's the 402, divide by the total number of people without the disease, well, that's 483. Return or enter, and we see it's 83%. Now, what do we do with these results? Well, we say that this was a study. It was a group of subjects taken at random, hopefully, from a population. And we need to understand from this research, can we use these results as far as the population is concerned? So let's just be naive at the moment and say that we can. And let's just look at the numbers, the proportions themselves as probabilities. So we can say, well, if we were to use this test, what can we expect? So what we're expecting that if I just looked at everyone in my population with the disease. Imagine I knew and I just selected everyone in the population with this disease. What is the probability that this test is actually going to pick them up correctly? In other words, return a positive result. Well, that's only going to happen in 69% of cases. But if I just to select from the population, imagine somehow I knew everyone who didn't have the disease, in 83% of them, I could think that this test is going to return a negative result, correctly indicating the fact that they have an absence of disease. And in real life, we have to decide what is more important for us. Is it sensitivity or specificity? Would I rather have something with a very high sensitivity, so it's going to pick up everyone with the disease, or do I want high specificity? Do I want it to pick up everyone without the disease? And you have to be in that scenario to make that decision. It depends what's more important. Unfortunately, it's very rare to find a test that is 100% sensitive and 100% specific. There's usually a little bit of a trade-off there. Now, we use sensitivity and specificity, as I say, to decide, are we going to use a specific test? But now imagine we did do that test. We subjected someone to that test, and the results now come back. They're going to come back either positive, the disease is there, negative, the disease is not there. But is that so? And what this really, really depends on is the prevalence of the disease in the population. So imagine a disease that is very, very rare. If I were just to take someone at random from that population, the chances of them having that disease are very, very low. And you might then think correctly that the positive predictive value of this test would be low. If it came back positive, it's still unlikely that someone would really have that disease because it is so rare in that population. So let's have a look at how to calculate positive and negative predictive values. As mentioned, we really need to know the prevalence of the disease. So let's write prevalence. And the prevalence is the snapshot. Imagine I could look at the whole population in one instance and know what proportion of people actually have that disease. Now, those are difficult and it's not always accurate, But imagine that we do know, and that's in our instance, we're going to say it's 0.05. So let's just imagine that in our population, 5% of the people have this disease. That's still quite rare. 95% of people do not have that disease. So can we use our data? Can we use the data to consider or create a calculation or do a calculation that we do have a positive and negative predictive value? Now, positive and negative predictive values are difficult to calculate. So what I'm going to do here on the right-hand side, I'm just going to do a couple of helper calculations. Let's put it like that. Positive predictive value. And let's go down a little bit. Let's have negative predictive value. So as far as the positive predictive value is concerned, there's a couple of things that we need. As far as the equation is concerned, please look up this equation, look in your notes, or look in a textbook. There's a numerator and there's a denominator. So I'm going to store these things separately as calculations that I can do rather than doing the whole calculation as a formula in one cell, and I might type something wrong and it goes awry. So let's think what goes in the numerator for positive predictive values. So in the numerator is sensitivity times prevalence. So let me just expand that. I'm just going to click between the I and the J there, and that expands that I column for me so I can see everything. So that's going to go in the numerator for positive predictive value. It also goes in the denominator, but in the denominator I have an addition of two little expressions. The first expression is the sensitivity times prevalence, but I also have something else. I'm adding to that something else, and that thing that I'm adding is actually the product, the multiplication of two expressions. And they are 1 minus the specificity and 1 minus the prevalence. And it's the product of those two that is one of the things that I'm doing the addition on as far as the denominator is concerned. Let's look at negative predictive values. Here we'll have specificity times 1 minus the prevalence. That's going to go in the numerator. And again, I have two expressions that I want to add to each other in the denominator. One of them is indeed this specificity times 1 minus the prevalence. And I also want to add 1 minus the sensitivity times the prevalence. So please have a look at those equations. There we go. I'm just going to click between the I and the J just to expand that column even more. So I know what I need for these two calculations. So let's calculate these things. What is sensitivity times the prevalence? So I'm going to do that calculation right there. So it's equals the sensitivity we've just calculated is right there. The multiplication symbol, I'm holding down Shift and hitting the 8 on my keyboard, so I get a little star. That's multiplication. And the prevalence I've got right up there. And F2, I'm going to click on that. And I'm going to hit Enter or Return. So we see sensitivity times prevalence. So what is 1 minus the specificity? Well, I'm going to say equals 1 minus, and we calculate the specificity right there. Click on that, enter, and I see what that is. And lastly, I need 1 minus the prevalence. So I'm going to say equal 1 minus the prevalence right there, and out pops that result. Let's look at what we need for the negative predictive value. So I'm going to say equals specificity I've got right there, specificity times, but now I've got to remember PEMDAS. Remember, there's an order of arithmetical operations, and multiplication is going to happen before subtraction. So I better use some parentheses because that's higher up the order. 1 minus, I'm going to click on 0.05, the prevalence, close my parentheses, done. Let's do 1 minus sensitivity, 1 minus, I'm going to click on sensitivity. There we go. And lastly, it's just the prevalence. So I can say equal and just click on the 0.05. So it's all there for me. So let's calculate this positive and negative predictive values. So remember that equals, this is what is in my numerator, and I'm going to divide by, and there's two things I want to add in my denominator. So I'm going to put all of that inside of a set of parentheses. And that is this same value, I'm going to click it on again, plus the product of these two. Now multiplication is going to happen before addition, so I don't have to use any more parentheses. It is just this one, that is that 1 minus specificity times 1 minus prevalence. I can simply close my parentheses and I can hit return. And I see a very low positive predictive value, only 17.8%. We'll talk about that. Let's do negative predictive value. That's going to equal, and there's my numerator, the specificity times 1 minus the prevalence. Click on that. Divide by, I want to add two things, and so I'm going to use a set of parentheses. First part of my addition is going to be this very same value, specificity times 1 minus the prevalence, plus, now the product of these two, sensitivity, 1 minus sensitivity I should say, times the prevalence. And I'm going to close my parentheses, hit return, and I see 98%. And there we have it, a positive predictive value of 17.8% and a negative predictive value of 98%. So let's just talk about it, the positive and the negative predictive value. Well, the positive predictive value is really low. If this test comes back positive, it does not mean that this person really has the disease. We see that it's only 17.8%. That's as low as this probability is. Why? Because the prevalence in the population is so low. If you take someone at random, they probably don't have the disease. 95% of them don't have the disease. The negative predictive value, though, is very, very high. Again, because the prevalence of the disease is so low. Much more likely that someone doesn't have the disease. And hence, when this test comes back negative, we can be very sure in telling this person that this disease is not there. Now, we've used these metrics, at least, in terms of a new test, but this applies everywhere. Let's look at manufacturing, for instance, just for fun. If you have a manufacturing line, there is going to be some defects in that manufacturing process. So what would happen or could happen is that some of the product are taken off the line at random, small sample, and they get analyzed to see if they're defective or not. But imagine this is time consuming, it takes a lot of time, money, effort, human effort, etc. And maybe there's a new test to test for whether this product is defective or not. And we want to compare that to the old gold standard that really showed whether a product is defective or not. How does this new test measure up? What is the sensitivity, specificity, positive and negative predictive values? And then in machine learning, specifically if we have a binary classification problem, we'll see how well our machine learning model does. We'll create a confusion matrix, which looks very much like what we've seen here, and we can calculate these same metrics to determine how well our machine learning model is doing. So there you go, metrics, sensitivity, specificity, positive and negative predictive values. You know how to calculate them. It's quite easy here in Excel, but you also know how to interpret these results.